Hello students. See, in today's session we are going to study the point that is Gibbs energy. Say how Gibbs energy is related with the enthalpy and entropy of system as well as with the temperature. That we all know about this spontaneous process, the processes which takes place on its own, that have the natural tendency to occur on their own, and there is no any external agencies required for their occurrence, is it? See here, one more thing we know that, see here, we have to just determine delta S system, delta S total for predicting the spontaneity of a reaction, because see, as we know, that is the equation delta S total is equals to delta S system plus delta S surrounding. And here for a spontaneous process we have just studied that when delta S total becomes positive, greater than 0, then it is a spontaneous process. Means that is, to predict the process to be spontaneous, we must know that is delta S system and delta S total, is it? So we are more interested in the system than surrounding. That is, it is therefore convenient to consider the criteria of spontaneity in terms of a thermodynamic property of a system alone, is it? So it is convenient to consider the criteria of spontaneity in terms of thermodynamic properties of system alone. So this problem was solved by J.W. Gibbs, introducing a new thermodynamic function or property called Gibbs energy, and it is denoted by G. So Gibbs energy is defined as, or it is given as, G is equals to H minus Ts, where H is the enthalpy of the system, T is the temperature, and S is the entropy of the system. As the enthalpy H, temperature T, and entropy S are the state functions, so G is also a state function which depends upon the initial and final state of the system. Now from this first equation, that is the change in Gibbs energy at a constant temperature is given by delta G is equals to delta H minus T delta S. So this equation shows the change in Gibbs energy. Okay, so this is all about the Gibbs energy. Now let us see about Gibbs energy and spontaneity. See, Gibbs energy and spontaneity. In the previous point we have seen about the Gibbs energy, that is G is equals to H minus Ts, and the change in Gibbs energy delta G is equals to delta H minus T delta S, is it? Now the point is Gibbs energy and spontaneity. Okay, see here, the spontaneous process that you know, is it? Now let us see how the spontaneity of a system can be explained in terms of Gibbs energy. We have seen how the spontaneous process are explained in terms of entropy change, is it? If the entropy change delta S is greater than 0, the process is a spontaneous process. If delta S is less than 0, then the process is non-spontaneous process, and the delta S is equals to 0, then the process is at equilibrium, right? Now the spontaneity in terms of the Gibbs energy, as we know, the delta S total is equals to delta S system plus delta S surrounding, according to the second law of thermodynamics, is it? Now delta S total is equals to the sum of these two entropies, system and surrounding. Now henceforth this delta S system we are just taking as simply delta S system as delta S. So the equation as delta S plus delta S surrounding, it is for delta S total. Now from the second law of thermodynamics, delta S total is always greater than 0. Entropy increases in a spontaneous process. Now see here, if delta H, the change in enthalpy of a system, if it is positive, Then for the surrounding it is negative. As the value of the change in enthalpy is same but with opposite in sign for system and surrounding. Therefore we can write according to this equation delta S is equals to Q upon T, that delta S is equals to delta H upon T. Like this we can write delta S for surrounding can be written as, to substitute here, delta S surrounding is equals to minus delta H upon T, like this way, delta S. If delta H is positive for the system and the negative, the same value is negative for the surrounding. That's why delta S surrounding is equals to minus delta H upon T. Now if we substitute this value delta S surrounding here in this equation 1, the equation 1 will become delta S total is equals to delta S minus delta H upon T. Rearranging this equation, that means multiplying by T throughout this equation, the equation will become delta S total is equals to delta S T delta S minus delta H. Okay, simply we have multiplied throughout by T. Okay, now again if just I multiplied, see here I just multiplied here by minus sign throughout, minus T delta S total, these two terms becomes like this after multiplication with the minus sign. This becomes minus, this becomes plus. So delta H, I can see we can write like this, delta H minus T delta S, right? The equation after multiplication with minus sign, the equation is became like this. Now see, comparing this equation number 2 with the equation of delta J, in the previous point we have seen the change in enthalpy is written change in Gibbs energy can be written as delta J is equals to delta H minus T delta S. The RHS of the both equations are same, so we can write this, the two are equal, so delta H is equals to minus T delta S total. Okay, so this is the equation we have just deduced here, and this is the equation of the previous point, that is the equation for the change in Gibbs energy, which is equals to delta H minus T delta S, and this is equals to the RHS of this equation second, right? So LHS must be equal, delta J is equals to minus T delta S total. So this is the equation relation. So this is the relation between delta G and delta S. See again, keep in mind this is the relation between delta G and delta S, is it? Now from this relation at a constant temperature, from this relation we can explain the spontaneity in terms of Gibbs energy, as below. For a, see, we have seen already for a spontaneous process, if entropy increases then the Gibbs energy decreases, because the both, that is the change in Gibbs energy and change in entropy, are related to each other with the minus sign. If one is decreases then the other will be increases. See, from the second law of thermodynamics, for a spontaneous process if entropy increases then the Gibbs energy decreases from this relation, we can see, is it? So from the above relation, the spontaneity in terms of Gibbs energy can be explained in this entropy change. Previously we have explained that the delta S total when greater than 0 the process is spontaneous, delta S total is less than 0 the process is non-spontaneous, and the process that is delta S total is equals to 0, the process at equilibrium, right? So for a spontaneous process delta S total is greater than 0, that we have studied in the previous points. From this equation the delta G must be less than 0. If one is positive then the other will be negative from this equation. See, for a spontaneous process if the entropy increases then the Gibbs energy decreases. For a non-spontaneous process if delta S total is less than 0 then the delta G is greater than 0. That means for a non-spontaneous process the delta S total means the entropy change decreases for a non-spontaneous process, and the same time the change in Gibbs energy increases. For the process is at equilibrium, if the delta is total 0 that we have seen, then the delta G is also 0 from this equation. So this is the explanation of the spontaneity in terms of the Gibbs energy. Say spontaneity and the change in enthalpy and change in entropy. The spontaneity and the relation between, that is the enthalpy and change in enthalpy and change in entropy, that is which decides the sign of delta G, change in enthalpy. That we know the equation for the change in enthalpy, delta G is equals to delta H minus T delta S. Now in this equation is predicted at constant temperature. Now here that is temperature determines the relative contribution of delta H and delta S towards the change in enthalpy delta G. Okay. Now depending upon this, the reactions can be categorized into 4 categories here. Suppose from this, if delta H and delta S both are negative, delta H and delta S are both negative, then delta G, change in enthalpy, will be negative. Is it? Only when delta G is more negative than delta S. This is possible at low temperature. See here, if delta H and delta S both negative, then ultimately delta G will be negative, and it is possible only when delta G is more negative than T delta S. This is possible at low temperature, and at low temperature, if this is possible, then being delta G negative, the process is spontaneous process. Now secondly, delta H, if delta H and delta S both are positive, delta G will be positive. Only if delta S is greater than delta H. If delta S, this term, is greater than delta H, this is possible at a high temperature. This is T delta S becomes greater than delta H at high temperature, and being delta G is positive, becoming positive, the process is categorized as non-spontaneous process. Now if delta H is, one is negative and another is positive in these two cases. First case both were negative, second case both were positive. In these two cases, one is negative, another is positive. If delta H is negative and delta S is positive, then ultimately delta G is negative regardless of the temperature. Is it? See here, delta G, if it is negative, this term becomes negative, and if this is positive, being this is negative sign, the term T delta S ultimately will become negative. That's why delta G becomes negative, and the process will be a spontaneous process regardless of the temperature. For all the temperature, the process will be spontaneous. Now for delta H is positive and delta S is negative, if this term is positive and this term will be negative, the ultimately delta G is positive, because delta S negative becomes positive, and the whole value for the delta G becomes positive, and the process will be non-spontaneous for all the temperatures. Okay, so this is all about the spontaneity and the sign of the delta G depending upon the temperature, delta H and delta S. Now temperature of equilibrium is one term is given in the textbook. So at equilibrium, delta G is equals to 0. We know the equation, this change in enthalpy, that is change in Gibbs energy, delta G is equals to delta G minus T delta S. If at equilibrium delta G is equals to 0, then the equation delta G is equals to delta H minus T delta S is equals to 0. So we can write delta H minus T delta S is equals to 0. So rearranging this equation becomes T delta S is equals to delta H. So T is equals to delta H upon delta S. Okay. So here the temperature at which the change takes place over from spontaneous and unspontaneous behavior occur. Is it? So here actually for the calculation of temperature T, that is delta H and delta S are assumed to be independent of the temperature, and if the dependence of delta H and delta S is considered, then there is no significant error for the moderate temperature range. Is it? So this is the temperature of equilibrium. Okay. See students, the next point, the Gibbs function delta G and equilibrium constant. Okay, the relation between the delta G and equilibrium constant Kc and Kp. Now Gibbs energy change for a chemical reaction simply given as delta G is equals to delta G naught plus RT ln Q, where delta G is the standard Gibbs energy. Okay. Now see, Q is a reaction quotient which is equivalent or analogous to equilibrium constant K. See, we know that equilibrium constant K, is it? The K reaction quotient is analogous to equilibrium constant, and it involves the non-equilibrium concentration. The equilibrium constant K involves the concentration at equilibrium exactly, but Q, which is considered here, which is taken here in this equation, it involves the non-equilibrium concentration of the reactants and products, or if the reactants and products are gaseous, then these are non-equilibrium partial pressures. Okay. Now see, consider the general reaction A times of A, B times of B, it gives C times of C plus D times of D. Now this Q reaction quotient, which is equivalent or analogous to equilibrium constant, is taken here, substituted here in this equation. Delta G is equals to delta G naught plus RT ln C raised to C into D raised to D divided by A raised to A into B raised to B. See, this term is the term of reaction quotient QC. Okay, this QC is equals to the product of products divided by the product of concentration of the that is the product of concentrations of the reactants. Okay, see, this QC is the ratio of the product of concentration of the products to the product of concentrations of the reactants. So delta G is equals to delta G naught plus RT ln Q is this value, which is Q as QC in terms of concentration. Or if this equation is in terms of partial pressure, if Q as QP, then equation is written as delta G is equals to delta G naught plus RT ln, that is partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B. Okay. Now when reaction reaches at equilibrium, then the delta G becomes 0, delta G equals to 0, and QC becomes KC, because QC and KP are non-equilibrium concentration and partial pressures. If it is equilibrium condition, then we can just take Kc and Kp, the equilibrium concentration, that is the equilibrium constant Kc and the equilibrium constant Kp. Now as delta G is 0, in this equation the equations will change as 0 is equals to delta G naught plus RT ln Kc. Now instead of Q, it is Kc at equilibrium for equilibrium condition. Now another is in terms of partial pressure, 0 is equals to delta G naught plus RT ln Kp. So rearranging these two equations in terms of concentration and in terms of partial pressures, delta G naught is equals to RT ln Kc, and delta G naught is equals to RT ln Kp. For the logarithmic use, the equations becomes delta G naught is equals to 2.303 RT log of Kc in terms of concentration, equilibrium concentration. Delta G naught is equals to 2.303 RT log of Kp in terms of partial pressures. So these two equations gives the relation between the standard Gibbs energy and the equilibrium constant Kc and Kp. So this is the end of the all the points of this unit, chemical thermodynamics. Now see, numericals are left. See, numericals, see, for the numericals we will take the session on Zoom app. Okay, we will need, I think, 2 to 3 Zoom sessions for the numericals for this chemical thermodynamics. So after this we will just go for the next unit. Meanwhile, I will just inform you when we are going to conduct the numericals of this chemical thermodynamics. Okay, best of luck and have a nice day.